Hello everyone. So in today's class, we are going to be continuing again with the scales of turbulent motion and focusing on the Kolmogorov spectra. So in the last class, what we did was we started with the 1D spectra, which was derived from the autocorrelation function for isotropic turbulence. So that applied only to isotropic turbulence. It was basically done in order to get a better understanding of how the spectra are related between the 1D spectra and the energy spectrum function. So the energy spectrum function contains the energy in all the directions, right? But the 1D spectra, we are only talking about the longitudinal direction or the transverse direction. E11 for the longitudinal direction and E22 for the transverse direction. So that would be related to the longitudinal autocorrelation function or the transverse autocorrelation function. And E of kappa would be the total, sort of like a 3D spectra, except it is a function of a wave number magnitude. Now, here what we are going to do is we are going to be focusing more on E of kappa. Obviously, we'll come to the 1D spectra in today's class as well. But we're going to start with what is called the Kolmogorov spectra. As in, based on the Kolmogorov hypothesis, can we come up with a function for the Kolmogorov spectra? Can we see what is called a model spectra looks like? So according to the Kolmogorov's hypothesis, in any turbulent flow, again at a sufficiently high Reynolds number, because all of this applies only when the Reynolds number is really high, the high wave number part of the velocity spectra, it adopts universal forms, isn't it? That was one of the first hypotheses laid out by Kolmogorov. As in, all the large scales are anisotropic, they are not universal. They depend on the flow, they depend on the scale of the flow. But after a certain demarcation, some energy containing range, isn't it? Some energy containing range, say 1/6 L0 is how we assumed it at that time. Less than that, all scales are universal. And what? They depend on epsilon and nu. That was his hypothesis, isn't it? And then he further divides it into two ranges. We'll come to that, the inertial subrange and the dissipation range, but we'll come to that. But keep in mind, this is the first hypothesis that he laid out. Like below a certain demarcation, 1/6 L0 as we assumed it at that time, less than 1/6 L0, we have scales that are universal equilibrium range as we called it. We'll show it in a schematic as well in today's class. So for any turbulent flow at a sufficiently high Reynolds number, the Kolmogorov hypothesis applies to velocity field on the small length scales, specifically in the universal equilibrium range. That is the one that is beyond the energy demarcation length scale. So that is the 1/6 L0, isn't it? LEI. So anything less than LEI, which also in terms of wave number corresponds to kappa greater than kappa EI. Because remember, kappa is 2 pi over L. That's how they are related. So higher the length scales, lower the wave number. So large length scales correspond to lower wave numbers, and small length scales correspond to larger wave numbers. So you have kappa greater than kappa EI, which is basically equal to 2 pi over LEI. So larger than kappa EI, you have the universal equilibrium range, or less than LEI, you have the universal equilibrium range. Both mean the same thing. Now, there was also, the next was a local isotropy hypothesis, as in the velocity statistics pertaining to the universal equilibrium range are isotropic, and this again corresponds to kappa greater than kappa EI. This again corresponds to kappa greater than kappa EI or L less than LEI, isn't it? So that is the local isotropy hypothesis. Now, according to the first similarity hypothesis, velocity statistics pertaining to the universal equilibrium range have a universal form that is uniquely determined by epsilon and nu. It only depends on the dissipation rate and the viscosity. It is uniquely determined by epsilon and nu. That means for kappa greater than kappa EI, E of kappa, the energy spectrum, only depends on epsilon, nu, and of course kappa, because it is a function of the wave number, isn't it? So it would depend on kappa. Throughout the range, it depends on kappa. We saw a model spectra earlier where it depended on kappa squared, isn't it? If I go back, it depended on kappa squared, it depended on kappa to the minus 5/3. When we wrote the function here, look at this. Here, we started with the 1D spectra, but you had E of kappa being equal to Ca kappa to the minus p. What did I say then? C is a constant, A is some kind of normalization function, so we'll get to that. But it varies with kappa, that is for sure. E of kappa varies with kappa. E11 of kappa 1 varies with kappa 1, and E22 of kappa 1 varies with kappa 1. So they vary with kappa, they vary with the wave number. There is a constant that is associated with it, and there is also a normalization function that is associated with it. Possibly, this normalization function, in the case of the universal equilibrium range, is a function of epsilon and nu. Couldn't it be? When we talked about the energy spectrum function during this part of the class, we did not say what A was, but now trying to relate it to Kolmogorov's hypothesis, where Kolmogorov says that E kappa is a universal function of kappa, epsilon and nu. So we have the kappa function that is there. We have a constant that is there. What about A, the normalization factor? It is possibly a function of epsilon and nu. That is what we are going to be dealing with in today's class. Okay, so let's use epsilon and nu to non-dimensionalize. Okay, purely on a dimensional basis, we could write E of kappa as epsilon nu to the fifth, the whole thing to the 1/4 times phi of kappa eta. So here what I have done is, I am writing it as some kind of a function, phi of kappa eta, which is non-dimensional. So it does depend on kappa, correct? But I'm writing it as a non-dimensional function multiplied by epsilon nu to the fifth, the whole thing to the 1/4. This is purely on dimensional basis. The energy spectrum function is the energy per unit mass. So I am using Kolmogorov's hypothesis, which states that in the universal equilibrium range, it only depends on epsilon and nu. So I'm using those two values to write the energy spectrum function. And I have a non-dimensional function there because it does depend on kappa, and I am making it non-dimensional by including eta in there. Remember, kappa has units of 1/meter. Eta is the Kolmogorov length scale, which has units of meter. So kappa eta would be non-dimensional, isn't it? So phi of kappa eta is a non-dimensional function. And this is called the Kolmogorov spectrum function. Now, this can also be written as U eta squared eta phi of kappa eta. How do I get that? Right? How do I get that? So let's try to see how that can be obtained. So I have E of kappa is epsilon nu to the fifth, the whole thing to the 1/4, phi of kappa eta. Okay? Now I know from Kolmogorov scales, eta is nu cube over epsilon to the 1/4, and U eta is epsilon, it is epsilon nu to the 1/4. Now what I'll do is, in this function here, I have epsilon to the 1/4 and nu to the 5/4. Okay? This is what I need to obtain. Let me try. Let me use this, and I will have nu to the 3/4 is equal to eta epsilon to the 1/4, isn't it? So, and then what I'll do is, I will use epsilon from here. So I have eta and epsilon from here. then what do I have? I have epsilon to the 1/4, which is u eta over nu to the 1/4. Okay, so that means I take nu to the 1/4 to the left hand side, and I have nu to the 1/4 times nu to the 3/4, which is nu. So nu is equal to u eta eta. Okay, that's that. And then what I'll do is, now here is what I do. From here, I take epsilon to the 1/4. Now I'm going to try and solve for epsilon. So epsilon to the 1/4, so this is again from here. This is again from here. Epsilon to the 1/4 is nu to the 3/4 divided by eta, isn't it? And then I'm going to use this again to derive to obtain an expression for nu. So nu to the 1/4. So then here what I would have is, I would have nu to the 3/4, isn't it? So that would be u eta cube divided by epsilon to the 3/4, right? And then 1 over eta. Then epsilon to the 3/4 goes to the left hand side, so epsilon to the 3/4 times epsilon to the 1/4, that becomes epsilon. So I have epsilon equal to u eta cube divided by eta. There you go. So I have nu is equal to u eta eta and epsilon equal to u eta cube over eta. So now this part here, I derive an expression for that. So epsilon to the 1/4 times nu to the 5/4 is equal to u eta cube over eta, obviously to the 1/4, multiplied by nu to the 5/4. So that is u eta eta to the 5/4. And then I will have u eta to the 3/4 and u eta to the 5/4. I use that, it becomes u eta squared. Then on the bottom, I have eta to the 1/4, and then I have eta to the 5/4 on the top. So 5/4 minus 1/4 is 4/4 or 1. So that would be u eta squared eta. So essentially, E of kappa is epsilon nu to the 5th phi of kappa eta, which is also equal to u eta squared eta phi of kappa eta. Isn't it? Two different expressions. The first one, I got it pretty much on dimensional basis, using epsilon and nu, using Kolmogorov's hypothesis, using the fact that Kolmogorov hypothesized that the universal equilibrium range depends only on epsilon and nu. I used that to write it as this function. And then I use the Kolmogorov's functions, as in the Kolmogorov scales, to write it in terms of the Kolmogorov u eta squared times eta. So I hope this is clear now. Now, let's see. If I go back, so this is what I wrote, right? The energy spectrum function is u eta squared eta times psi of kappa eta. Now, if I think about it, I use this based on Kolmogorov's hypothesis that the universal equilibrium function only depends on epsilon and nu. There was another hypothesis by Kolmogorov, the fact that beyond the dissipation range, it only depends on epsilon and not on nu. It only depends on epsilon and not on nu. So what if I write the energy spectrum function as dependent on only epsilon and kappa? So if I use epsilon and kappa alone to write the non-dimensionalization, to write the E of kappa, then I will have it as epsilon to the 2/3, kappa to the minus 5/3, and psi of kappa eta. So another non-dimensional function, So the first one, I wrote it in such a way that it depends on both epsilon and nu. The second one, I wrote it in such a way that it depends only on epsilon and kappa. So I have it as epsilon to the 2/3 and kappa to the minus 5/3 psi of kappa eta. Now if I relate this two, how do I relate these two? I just have to divide those. If I divide those, and what I'm going to do is I'm going to try and show it to you what I get. So E of kappa is U eta squared eta psi of kappa, phi of kappa eta, and E of kappa is also epsilon to the 2/3 kappa to the minus 5/3 psi of kappa eta. If I derive these two, what do I get? Psi of kappa eta is U eta squared eta divided by epsilon to the 2/3 kappa to the minus 5/3 phi of kappa eta. Isn't it? Now, what is epsilon to the 2/3? Okay, what is epsilon to the 2/3? Epsilon to the 2/3, from here, I can use this to get it. So I will write this as U eta squared eta divided by epsilon to the 2/3, which is U eta cube over eta to the 2/3, and then kappa to the minus 5/3 phi of kappa eta. So I will have U eta squared, and here what I'll have is U eta squared again, and then on the top I'll have a eta and the eta to the 2/3, and then kappa to the 5/3, and then phi of kappa eta. So these two get cancelled, and what I have is kappa eta to the 5/3, isn't it? Because I have eta times eta to the 2/3, which is eta to the 5/3, and then multiplied by phi of kappa eta. So this is my psi of kappa eta. So this is how the universal functions are related to each other. One universal function used for the spectrum where it only depends on kappa and epsilon. And the other one, it is used for a spectrum function where it depends on epsilon and nu. And they are related in this form. Kappa eta to the 5/3. So if you think about it, this is what is shown here. The universal functions are related by psi of kappa eta is kappa eta to the 5/3 phi of kappa eta. This is how the two universal functions are related. And this corresponds to the universal equilibrium range. So kappa greater than kappa ei, or if you just multiply eta on both sides, you get kappa eta greater than 2 pi eta over LEI. Remember, kappa EI is 2 pi over LEI. That's how I get this from. So this is just multiplied by eta on both sides, and I have kappa eta greater than kappa EI. So what we are trying to say is, beyond that range, and if you write it in a normalized fashion, it is beyond kappa eta, because kappa eta is normalized. So beyond kappa eta, this normalization function is related to the other one normalization function is related to the other normalization function in this form. One normalization function associated with the energy spectrum function that only depends on epsilon, whereas the other depends on both epsilon and nu. That's it. Okay, that is what we derived here. And this is the schematic that I was talking about. This schematic, if you see here, I have the energy containing range on the low wave number side, and that is, I have the highest wave number, which is kappa 0, which is 2 pi over L0, isn't it? And the energy demarcation length scale, which is LEI. So the wave number corresponding to that is kappa EI. This is kappa 0. So everything here is the energy containing range. This is the universal equilibrium range. This is the energy containing range, ER, UER. And the universal equilibrium range itself is divided into two sub-ranges. Remember, I have a LDI, which is again much less than L0 and much greater than eta. LDI, or the demarcation of the dissipation range. So the universal equilibrium range is divided into the inertial subrange, IR, isn't it? Actually, since it is the inertial subrange, I'm going to call it ISR, inertial subrange. And beyond here, it is the dissipation range, dr. Okay, so this is kappa di corresponding to the length scale of LDI, and then going all the way to the Kolmogorov scale, k eta, kappa eta, which is 2 pi over eta. So the dissipation range only depends on epsilon. It does not depend on nu. The entire equilibrium, universal equilibrium range only depends on epsilon and nu. That is the reason why we took two kinds of functions. One where it depends on epsilon and nu, and the other one where it only depends on epsilon. And that is the dissipation range, is that range where it only depends on epsilon. Remember, we took two spectrum functions, and those two spectrum functions, one of them depended on epsilon and nu, the other one depended only on epsilon. It is to correspond to the universal equilibrium range and the dissipation range. I hope this is clear. So the second similarity hypothesis applies to scales only in the inertial subrange, right? So that is scales that are much less than L0 and much greater than eta, the inertial subrange. It is much further from both ends, much less than L0 and much greater than eta. And then L here, which in the inertial subrange is basically between LEI and LDI, isn't it? LDI and LDI and LEI. So KEI and KDI. That's what this is. Kappa is less than KDI, kappa is less than kappa DI, or kappa is greater than kappa EI. In terms of kappa eta, you can write it in this form. Okay, how can we do that? So if you think about it, I have my L, my inertial subrange, which is much less than L0 and much greater than eta, isn't it? Or I have it as L being less than LEI and greater than LDI, which in terms of wave numbers is kappa less than kappa DI, right? Kappa less than kappa DI and greater than kappa EI. That is what is shown here, isn't it? So that's what I have. Now let's take this part, okay? And I take the inverse, then all the signs flip. Then what I'll have is 1 over eta greater than 1 over L, much greater than 1 over L0, isn't it? Then I multiply all sides by eta. Then I have 1 greater than eta over L, greater than eta over L0, isn't it? Now I have 1 over L here, which is proportional to kappa. 1 over L0 here, which is again proportional to kappa. So essentially what I'll have is 1 greater than kappa eta, which is much greater than eta over L0. That's how I get this equation. So in terms of kappa eta, we are writing it in terms of kappa eta because everything is, we are thinking about normalizing everything. When we wrote the energy spectrum function earlier as well, we wrote it in terms of kappa eta. That is why we are getting all these expressions in terms of kappa eta. Now, if you look at it in terms of this one here, okay, so if I just flip it and write it as KDI greater than KEI, then I can write it in terms of just multiply by kappa eta. Then I'll have kappa eta is greater than kappa EI eta, which is 2 pi over LEI eta, right? Kappa eta, and this is less than kappa DI, which is equal to 2 pi over LDI eta. So that's pretty much what I wrote here, right? Kappa eta is 2 pi over LEI. So everything I'm writing it in terms of kappa eta. Because if I look at my energy spectrum function, everything is in terms of kappa eta, normalized. Kappa is wave number, eta is the actual scale. Both of them multiplied together gives me a normalized value, a non-dimensional value. So I'm writing in terms of kappa eta. So I want to know how the kappa eta varies, say for example, in the inertial subrange. and kappa eta is much less than 1 and much greater than eta over L0 in the inertial subrange. Kappa eta is greater than kappa EI eta and less than kappa DI eta in the inertial subrange. That's what I'm saying. So here, what I've done here is I have looked at the energy spectrum function in terms of the entire universal equilibrium range by relating it to both epsilon and nu. And then for the dissipation range alone by relating it only to epsilon, obviously depending on kappa as well, in order to dimensionally match it. And then I related the two non-dimensional spectrum functions in terms of kappa. And I derived the fact that one of the spectrum function is kappa eta to the 5/3 multiplied by the other spectrum function. So that's how I have it. So everything for me is in terms of kappa eta, a non-dimensional value. And scaling is actually much better to see all these cases. So I hope this is clear. In the next class, we will go into the model spectrum actually and see how these functions change and how they are applied in terms of the model spectrum. Thank you.